All right, we're going to practice some condensing and evaluating logarithms, and then also expanding logarithms. So for this first one, log of 183, or log base 5 of 183, this is one where if you know how to get to the log where you can actually change your base in your calculator, feel free to do that, but our change of base formula will always work here as well. And so to calculate this, another way of doing this is just writing log of 183 over log, and this is using the common log, so it doesn't have its base is 10. We don't write a base for it, but you can write 10 if you really want to. Or you can use natural log in your calculator. Natural log of 183 divided by natural log of 5. I prefer natural log. So natural log of 183, close parentheses, divided by natural log of 5, close parentheses, would give me, and I'm going to round to 3 decimal places, 3.237. Again, your natural log button on your calculator is right next to your 4, and then regular log or common log is right next to your 7. Okay. For this next one, here, let's go do this one down here because this is a similar setup, right? Log of, I'm going to do natural log. Natural log of 194 divided by natural log of 16. Natural log of 194, close parentheses, divided by natural log of 16. And again, 3 decimal places. 1.899. I guess technically I should round up to 1.900. We don't do sig figs here. All right, for these ones, you have to do a little bit of work first, which is okay. All it means is that this, I'm going to combine or condense my logarithm first. So when I have subtraction between 2 logarithms or outside 2 logarithms, it turns into division instead of 1. So log base 5 of 75 divided by 3. And then I can simplify that a little bit. So that's log base 5 of 25. And then now I can actually calculate that by doing natural log of 25 divided by natural log of 5 in my calculator, which gives me the number 2. Same thing with down here. We're going to have to combine these first. This one's a little bit longer, so I'm going to move my constant multiples up first. So I'll get log of 9 plus log of 2 cubed minus log of 3. But then addition happens outside my logarithm, so that turns into multiplication instead of 1 logarithm. So I'll have log of 9 times 2 cubed. Oh, that's terrible. Let's write that over here instead. Log of 9 times 2 cubed. And then I still have this minus log of 3 happening. And then so then that turns into division. My subtraction between 2 logarithms turns into division instead of 1 logarithm. So log of 9 times 2 cubed over 3, which means log of, 9 times 24. And then this one's secret. You don't have to do change of base here because this is a common log and your calculator can just do those. So in your calculator, you can just hit LOG and then the number 24, and you'll get 1.380. Oh, this is chaos. So that was my final answer for that one. Final answer for this one. Okay, as long as you followed my instructions in the videos as you went, it should be okay. All right, so let's go ahead, and now we've got 8 problems where we're just going to expand our logarithms. And so in this one, you're basically trying to write it in as many logs as possible. And I'll show you how. So for this one, when we were condensing, we worked with the exponent parts first. So changing our constant multiples to exponents. Now we're going to do the opposite. That'll be our last step. So the first thing I'm going to do is I'm going to start breaking up my log as much as possible. So right now, for example, I see that between x squared and y to the 7th, I have multiplication occurring. So I know that multiplication inside of a logarithm turns into addition between 2 separate logarithms. So I can write this as log base 3 of x squared plus log base 3 of y to the 7th. And then there's no more multiplication or division happening inside of those. So I can now go ahead and these exponents can come down in the front and become those constant multiples that we've been working with. So now I'll have 2 log base 3 of x, and then that's the only thing that's in that logarithm now, so that's as simple as that one gets, plus 7 log base 3 of y. And we're done. Amazing. You know you're done when you have a variable in here that you can't do anything more with. Like that's not multiplying anything. It doesn't have an exponent. It's not anything is happening to that. So I know I'm done with that piece. All right, let's do this one. So the first thing I notice is that I have division occurring between these two pieces. So I'm going to go ahead and division inside of one logarithm turns into subtraction between two separate logarithms. So log base 8 of square root of x minus log base 8 of y cubed. And then be careful because this square root of x is secretly not a square root of x, right? Anytime you have x, there's your power, there's your index. So I can rewrite that with an exponential fractional exponent, and that's good because I want to be able to bring down exponents. So if I go ahead and I can rewrite that as x to the 1/2 power, and now I can go ahead and bring down those exponents as constant multiples. So this will be 1/2 log base 8 of x minus 3 log base 8 of y. So now I just have a regular x and a regular y, so I know I'm all done. All right, and these ones. All right, the biggest thing that's happening here is this division that's going on. So first thing, division inside of a logarithm turns into subtraction between two logarithms. All my stuff on top, my 4 and my x, goes in the first logarithm. Then I'm subtracting the second one, y to the 9th. And then this one I can technically break up further because it's 4 times x, right? There's not just a regular x here. So my 4 times x can be broken down even more. So I'll have log base 4 of 4 plus, because multiplication inside of a logarithm turns into addition between two logarithms, log base 4 of x minus, oh, and I guess the last thing we can do here is this doesn't have an exponent, this doesn't either, so I can go ahead and bring this down right up here. 9 log base y. Saves me from writing an extra step. All right, regular x, regular y, regular 4, done. All right, this one, I got division occurring is the biggest thing, right? It applies to all the variables. So the first thing I'm going to do is I'm going to rewrite division inside of a logarithm as subtraction between two separate logarithms or outside of the logarithms. All the stuff in the numerator is going to go in the first log. So I got the 4th root of x cubed and then y to the 7th minus log of z to the 8th. And then I can definitely break this one down farther, right? Multiplication inside of a logarithm turns into addition outside. So I'll have log of the 4th root of x cubed plus log of y to the 7th minus log of z to the 8th. And then I have some exponents I'm going to bring down. I also have an exponent here, right? Basically, we said if you have a radical, that's its power and its index, I can rewrite it as a fractional exponent. So I can rewrite this instead of x to the, or the 4th root of x to the 3rd, this is secretly going to be, not so secret anymore, x to the 3/4 power. So now these all are exponents I can bring down and have as a constant multiple. 3/4 log of x plus 7 log of y minus 8 log of z. Regular z, regular y, regular x, done. All right, with this one I got a nice natural log going on. That's an L, ln, not an I. So many people think it's an I. First thing that's happening is I have division occurring, so I have natural log of my numerator. Oops. And then I'll be subtracting. Division inside a logarithm turns into subtraction outside a logarithm of y squared z to the 7th. And then this one I know I can break down farther. Be a little bit careful here and I'll show you why. So I'm just going to bring down my natural log of x to the 5th. This minus applies to this logarithm. So if I break this logarithm down farther, I still have to make sure my minus applies to the whole thing. The way to make sure this happens is to, if I'm breaking this down, whatever you break it down into, make sure it goes in parentheses because that means that the subtraction will still apply to all pieces of it. So multiplication inside of my logarithm turns into addition between two separate logarithms. So natural log of y squared plus natural log of z to the 7th. And then now if you want to distribute that negative, you're more than welcome to. You don't have to though. So I won't, but you can if you want. These exponents you also could bring down to the front of each of their logarithms as constant multiples. So 5 natural log of x minus parentheses 2 natural log of y plus 7 natural log of z. The only difference that would happen is if you actually distributed that negative, your answer would look like this instead. It would have, the negative would be on the 2, and then that would be a minus. But you don't have to. You can leave it just like this. Okay. All right, in this next one, I got natural log of 7x cubed y to the 8th. All of that stuff is multiplying, so I know it's all going to change into addition between multiple logarithms. So I'll do the 7 first. Actually, let's do it all in a row. We're pretty pro. So it's multiplication here and it's multiplication here. So I'll have natural log of 7 plus natural log of x cubed plus natural log of y to the 8th. And then those have exponents, so those can come down and be constant multiples. So natural log of 7 plus 3 natural log of x plus 8 natural log of y. Woohoo! All right, 2 more. Let's see if we can do it. So in this one, we have log base 2 of division. So log base 2 of my numerator, which is just the number 1, minus my denominator, which is log of x to the 5th y cubed. And again, because I'm going to be splitting up this logarithm, make sure that negative applies to the whole thing. Log base 2 of 1 minus parentheses log of x to the 5th plus log of y to the 3rd, and then bring down those exponents. And done. Your last step, if you really wanted to, would be to distribute that negative, but you don't have to. All right, last one. This one's a doozy. So I see division is the biggest thing that's happening first, so let's do it. Log base 9 of the 6th root of x to the 5th minus log base 9 of y cubed. Ooh, we're going to need some brackets. I'm going to use brackets as a second set of parentheses, so that way I don't get confused in my parentheses. Y cubed, and then z minus 2 to the 7th. There's no difference between brackets and parentheses, they just look different, so it's easier to distinguish what's happening. This one can be broken down any further, and because it's after I'm subtracting this, make sure that the subtraction applies to the whole thing. So log base 9 of the 6th root of x to the 5th minus parentheses log base 9 of y cubed plus, because this was multiplication technically, log base 9 of z minus 2 to the 7th. This z minus 2 to the 7th is gross because you can't do anything with subtraction inside of a logarithm, so it just stays that way. All right, and then it looks like I got some exponents I can bring down. Exponent here, exponent here, there we go. And then remember, we can rewrite this instead of doing x, or the 6th root of x to the 5th, this is secretly x to the 5/6 power over index. And so that exponent can come down too. So you'll have 5/6 times log base 9 of x minus parentheses or brackets 3 log base 9 of y, it's just regular y now, regular x, plus 7 log base 9 of z minus 2. And we're upset because it's not a regular z, but we also know that subtraction inside of a logarithm makes our life hard, and we can't simplify that any further. Last thing you could do if you really wanted to is distribute that negative, but you don't have to. All right, nice job, guys. Those are all the examples I have for logarithms, so why don't you go ahead and go practice.